There are three things, A, B, and C, that we are going to do in the two graphs below. Let's start with A. And I'm going to separate that between a graph 1 and a graph 2. I'm also going to come up to the graphs and look at these different area portions. So here we might call this A1, the second portion A2, and finally third portion A3. Likewise, I'm going to call this A1. Now, A is area, means a positive quantity. So this triangle here would have a positive area. This is A2, a positive area, and this is A3. All of those are positive areas, not necessarily positive integrals. In part A, graph 1 wants us to find the total area. So let's say area total is equal to the A1 plus the A2 plus the A3. And all I have to do is appeal to some geometry to get those areas. The first one is a rectangle whose base is 4 and whose height is 2. And the second one, now I want to talk about this for a second. This is a trapezoid, and picture the trapezoid on its side. So here's one of the bases, and here's the other base, and then you can think of this quantity here as the height of the trapezoid that's on its side. And of course you should certainly know the area of a trapezoid is average the base times the height. So that's how I'm going to write this here. Base 1 would be the first blue distance of 2, plus base 2 is the blue distance of 3, and I'm going to average those bases times the height, which is the horizontal increment of 2. So this second expression in between these two plus marks here is that trapezoid. Finally, we have the rectangle A3, which is base of 1, height of 3. Put that all together, 8 plus 5 plus 3 equals 16. That is the total area bounded between the graph and the x-axis. The second graph, the total area, is again A1 plus the A2 plus the A3. We're only going to consider the positive quantities for area. The triangle has the area 1/2 base of 2 times height of 2 plus the next triangle 1/2 a base of 3 and a height of 1, and then the semicircle has pi radius of 1 squared, and that gets divided by 2 as we have just the semicircle, and we add all that up to get 7/2 plus pi over 2. That is the total area. Now for part B, graph 1, it says evaluate the integral from -3 to 4 of the function f of x dx. Now I hope you can see that this graph of graph 1 has a function that is always above the x-axis, and when the graph is always above the x-axis, the integral equals the area. So I would say the integral from -3 to 4 of f of x dx is equal to a1 plus a2 plus a3, which we already worked out to be 16 in part A, graph 1. Now let's take a look at graph 2. Here, the integral from -3 to 4 of f of x dx will equal, see, the area is positive, but it's below the x-axis, so we want the opposite of a1, and then the second area is above, so plus a2, and then the third area is below, so again back to minus a3. Remember, integral gives you net area. So we have a -4/2 for the first triangle, plus a 3/2 for the second triangle, minus a pi over 2 for the semicircle, and that comes out to be -1/2 minus pi over 2, which is a negative quantity. the integral can be negative. Now in part C, we're going to look at the total area in terms of integral pieces. The first one is pretty simple. Again, everything is above the x-axis. So we'll say the integral from -3 to 1 of f of x dx, that would be the first area, plus the integral from 1 to 3 of f of x dx, plus the integral from 3 to 4 f of x dx. Graph 2, the area total, in terms of the integral expressions, would be not the integral from -3 to -1 f of x dx. You see, that integral would give me a negative quantity. So I want to find total area, positive area, so I want to take the opposite of this negative quantity. So minus the integral from -3 to -1 f of x dx. Then we're going to add the integral from -1 to 2 f of x dx. Finally, I need to find the opposite of the integral from 2 to 4 f of x dx, because the integral from 2 to 4 gives us a negative quantity. This becomes positive. This becomes positive. Part A of practice 1 asks us to find the total area, and I think the areas bounded between the x-axis and the curve, which we'll call f of x, are pretty clear. So let's start off by finding the total area. So area equals, the first area portion looks like a triangle, so we have 1/2 base times height, plus then we have this trapezoid, which is laying flat, you might say. Average the base, so I have a 9 is one base and a 4 is the other base. I average the base times the height. In this case, the height is 2. Then I have another semicircle, so 1/2 pi times the radius squared. And then I have another triangle, which is 1/2 base times height. Simplified a little bit, and so this area here is 5, this area here 13, 9/2 pi, and finally 10. Add those all up together and we get 28 plus 9/2 pi. That is the total area. For parts B through E, you might want to press pause, give it a try, and then come back and let's talk and check some answers. In part B, the integral from -11 to 10 of f of x dx, we're going to find this integral by appealing to the geometry. So we have the 5 minus the 13 plus the 9/2 pi minus 10. That equals -18 plus 9/2 pi. In similar fashion, the integral from 0 to 10 of f of x dx is 9/2 pi minus 10. In part D, -9 to -2, so that comes and cuts into this. So if I thought of 13 minus the little triangle, so 13 minus 2 as the area, then I would need to find the opposite because it's below the x-axis. So the answer to that is -11. Finally, in part E, this actually illustrates a property. You might notice that the bounds are going from a larger bound to a smaller bound, and the property says that we can switch them and go from the smaller bound to the upper bound as long as we make it the opposite value. So negative integral from -9 to 0 of f of x dx, and that's going to be the opposite of -13, which gives us a positive 13. Please complete the values for graph 2 in the practice, and in 3 seconds I will reveal just answers. 3, 2, 1. Answers. One notable answer being the last one. The integral from value to itself equals 0.